everyone, I am Akhilesh Kumar Shrivastava from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we have already discussed about several techniques related to the memory management. We have seen that there is a fixed partitioning scheme wherein we fix up the degree of the multiprogramming, meaning that we are fixing up the number of processes that can run at a given instant of time. We have seen the variable partitioning as well, which was not fixing the degree of multiprogramming. Depending on the processes coming in the system, we were allocating them to RAM, and the degree of multiprogramming was not fixed. It means by the time we can accommodate the processes in the RAM, we will keep doing that. Both of these schemes, the fixed partitioning scheme and the variable partitioning scheme, were subjected to the fragmentation. In the fixed partitioning scheme, there was internal fragmentation, and we were finding that there is a huge wastage of memory, and that was sheer wastage because we cannot utilize that memory for the other purposes. In the dynamic partitioning, because of lot of processes coming in and going out, the small holes were getting created. Those small holes altogether were able to accommodate a process if we are not accommodating them in the contiguous space. But since dynamic partitioning is a contiguous memory allocation scheme, we cannot that memory as well, or that the area of the memory occupied by those holes. The scheme to utilize those memory would be the compaction, but the compaction was a very costly job, because when the compaction is performed, the CPU is continuously busy in doing that and does not perform any other execution. Thereafter, we have seen a better scheme of non-contiguous allocations, which were the segmentation scheme. But once again, we have seen that the segmentation scheme was also subjected to the external fragmentation. Another scheme, which was supposed to be the best scheme out of all the available ones, was the paging scheme, wherein we were dividing the processes into the equal size chunks known as the pages, and then the equal size chunks in the main memory as well, known as the frames. So, the pages were getting accommodated into the frames as and when the processes need to be executed. In this way, there was no wastage of memory, because the same size pages were getting accommodated in the same size frames. Yes, there was some fragmentation because of the last page, but that was negligible. We have also seen that how can we select the size of the page such that the wastage of the memory gets minimum in the case of the paging scheme. After that, we have seen the virtual memory scheme, wherein we were considering that we have a huge space wherein the processes can get accommodated. That actually is the part of the hard disk, those that is being treated as the RAM, and depending on the requirement of the process, the pages are brought from that space to the main memory. So, this was actually the concept of the demand paging. Whenever the page is required, that is brought from the main memory from the hard disk space to the RAM, and whenever not required, they are sent back to the hard disk. So, we have seen the scheme of the page replacement of the last term, and we are extending that scheme today. So, the outline of today's lecture will be that we will first see what are the various page replacement algorithms, then we will see the Belady anomaly, and the Belady anomaly is actually a phenomenon that occurs in the first in first out page replacement algorithm, and finally in today's lecture we will discuss about the page faults. Now, we have seen about the page replacement algorithms that we are not allocating the space for all the pages of a process to get into the RAM space. We are allowing only the limited number of the pages to come in, and because of this we will be able to accommodate large number of the processes in the RAM. This way we will be increasing the degree of the multiprogramming. So, whenever a page is referenced by the CPU, it means an instruction is referenced by the CPU and that lies in some of the page, that page is looked into the RAM. If present, we will be giving the instruction from RAM space to the CPU for the execution. Otherwise, we will declare that this is a page fault, because the page which is required is not present in the memory. Because of this, we will be bringing a page from the virtual memory space to RAM, and this may require the removal of one of the existing page in the RAM. Hence, this is called the page replacement. We have seen several page replacement algorithms on the last turn. We have seen the optimal scheme, we have seen the first in first out scheme, we have seen the LRU scheme. So, the first in first out scheme says that whenever a page is coming for the RAM to be for the RAM frames, then if a page is already there or all the frames which are allocated to the process are busy, then one of the page which is the oldest page is sent back to the RAM and a new page is brought back. So, this is the first in first out page replacement algorithm. In the LRU scheme, which is the least recently used algorithm, whenever a page is referenced, we actually put it on the top, meaning that that page is referenced just now, and the page which is not recently used or which is the least recently used, the new coming page will replace that. It means the recently accessed page will be retained, while the page which is not referenced for the long time will be sent back to the virtual memory space. The optimal page replacement algorithm will require that it should have a knowledge about the future references as well, and if in the near future a page is required, or if in the near future a page will be referenced, we will retain that page in the main memory, and those pages which will be referenced very late will be replaced with the new coming page. So, these are the three schemes that we have seen. There are more schemes available for the page replacement algorithms. For example, most frequently used, for example, LFU, least frequently used, most frequently used, and many more. We can also select a random algorithm for replacing a new page with a old page. We have also seen with the numerical that how the page faults are occurring. We were counting the number of the page faults. Let us say in a certain duration of the time there are x number of the page faults occurred, and there were total y number of the references. So, we will say that x upon y is the page fault rate. Now, we will see today the Belady's anomaly. To understand what the problem is, what is the Belady's anomaly, let us take a numerical and let us see that how the page replacement will work once with 3 pages, 3 frames, and then again with the 4 frames. So, let us say the reference string is 0, 1, 2, 3, 0, 1, 4, 0, 1, 2, 3 and 4. Let us say we have 3 frames and we are actually doing the page replacement with the optimal scheme. The page number 0 which is referenced is not present in the list. So, we will bring it. So, there is a page fault here. So, we are counting it as 1, and then 1 number page is also not present. So, the 1 number page will be brought from the virtual address space to this. So, 2 is the count, then the 2 comes and 2 is also not present. So, this again is a page fault. We will be bringing one of the page from the virtual address space to the main memory frames. So, 3 page faults have occurred till now. Now, there is a reference of page number 3. Since there is a reference of page number 3 and there is no more space to accommodate 3, one of the old page will be sent back to the virtual space. So, let us see which of the page we can send it. So, optimal page replacement algorithm suggests that we should find out which of the page will be referenced in the near future. So, since 2 is a page and 2 will be referenced at this point, and then 1 is a page, so 1 will be referenced here, and then 0 is the page which will be referenced here. So, immediately after 3, 0 will be referenced. It means 0 has to be retained, 1 will be referenced later. So, 1 has also to be retained, 2 will be referenced quite late. So, we will be replacing the 3 with 2. So, there is a page fault and we have done the page replacement as well. Now, there is a reference of 0 which is already present. So, there is no page fault, and then there is a reference of 1 and 1 is not present. So, we will be sending one of the page out. Okay. So, we will be sending one of the one of the page out, and then there is a page fault again. So you can see that with this scheme, when we are actually moving ahead with this scheme, the page faults are increasing. And similarly, let us say we have the reference with the 4 frames. So let us count the number of the page faults occurring because of the 4 frames. So here we have taken 3 frames, and then we are doing it again with the 4 frames. So when we are doing it with the 4 frames, so for 0 there is a page fault, then for 1 there is a page fault, for 2 there is a page fault, and then for 3 there is no page, there is a page fault, so we have counted it as 4. For 0 it is already present, so there is no page fault, and then 1, this is also present, no page fault. 4 is present, some of the page will be sent back to the virtual space. So what we can see that out of 3, 2, 1 and 0, 0 will be referenced here, and then 1 will be referenced, and then 2 will also be referenced, and 3 will be the late reference, or the reference of 3 will be very late. So we will be sending 3 and will be bringing 4. So there is a page fault and the number of page fault is increased. Similarly, we can find out the page fault in the other case. So here what is seen here, that the number of page fault with 3 frames is less than the number of page fault which occurred because of the 4 frames. So here we are actually mentioning the number of page fault with 3 frames is less than the number of page fault occurred with because of the 4 frames. Okay. Now why this is happening? You can see that when we are doing this page replacements, then when 0 is referenced in the case of the 3 frames and 0 is referenced in the case of the 4 frames, 0 is present in both the frames. Similarly 1 and 1, so both are present. 2 and 2, it is present when 3 frames were there, it is present when 4 frames are there. So you can see that all the pages which were there in the scheme where we are using 3 frames, and when we are using 4 frames, the pages are present. Similarly, you can see that 310 is present here and 310 is present here also. Similarly 0, 320 is present here, 320 is present here as well. 120 is present here and 120 is present here as well. So 410 is present here and 410 is present here also. It means that in every scheme, we can check with the other part as well. 410 is present here, 4, 1 and 0 is present in the 4 frames as well. Now 410 is present here, 4, 1 and 0 is present here. 2, 4, 1 is present here, 4, 2, 1 is present here. 3, 2, 4 is present here, 3, 4, 2 is present here. 3, 2, 4 is present here and 3, 4, 2 is present here. So all the pages which are present in the 3 frame scheme is available in the 4 frame also. That means it is following some property, and what we are saying that this is the stack property. So if a scheme follows the stack property, it means that the number of page faults with less number of the page frames will be less than the number of page faults occurred because of the high number of page faults. If you take this scheme only, the number of page faults with the this will be just the reverse. The number of page faults with 3 page frames will be greater than the number of page faults which occurred because of the 4 page frames. Let us take another example of the Validity Anomaly. Let us take the LRU scheme. So it will happen in the LRU scheme also, that the number of pages which were present in the 3 frames and the number of pages which are present in the 4 frames, the 3 frames will be subset of the 4 frames. Okay. For 0 there is a page fault, for 1 there is a page fault, for 2 there is a page fault, for 3 there is a page fault, for 0 there is a page fault because 0 is not present. So we will be sending the least reference page. So 1 is the least reference page, so we will be sending that and we will be bringing 0 here. Similarly for 1 is not present, so we will be sending 2 and we will be bringing 1. The page which is present at the top is the recently referenced page, and the page which is there at the last is the least reference page. Okay. So for 4 we will have to replace it with 3. So for 0, 0 is already present, so we are bringing 0 on the top. For 1 we are bringing 1 on top, there is no page fault in this case and there is no page fault in this case as well. For 2, 2 is not present, the least reference page is 4, we will be sending that out and we will bring 2 here. So there is a page fault. For 3 again 0 will be sent back and 3 will be brought here. So there is a page fault. For 4, the 4 is not present, so 4 will be brought here in the frames and 1 will be sent out. So if you count the number of the page fault here, 1, 2, 3, 4, 5, 6, 7, 8, sorry, here is this not the page fault, 8, 9 and 10. So the number of page faults which occurred because of the 3 frames is actually equals to 10. If we try to find out the number of page faults which is occurring because of the 4 frames, then this will be 0, a page fault, 1, there is a page fault, 2, there is a page fault, 3, there is a page fault, and then for 0, there is no page fault. So we just cross it. We are bringing the 0 on the top because this is recently referenced. For 1, there is no page fault, we are bringing the 1 on the top. For reference of 4, there is a page fault, so 2 will be sent back. So there is a page fault and the count of the page fault is increased to 5 now. And then for 0, 0 will be brought on the top, so there is no page fault. For reference of 1, 1 is already present, so no page fault. 2, yes, 2 will be brought here and 3 will be sent out, so the number of page fault is increased to 6 now. For 3, 3 is not present, so 4 will be sent and 3 will be brought in. So 7 page faults, and 4 is also not present, so 0 will be sent back and 4 will be brought here. So the number of page faults are 8. So you can see that the number of page fault with the 4 frames is equals to 8. Clearly you can see that the number of page faults with the 3 frames is greater than the number of page faults which occurred because of the 4 frames. Or you can say that if we increase the number of the page frames, then the number of page faults also decreases. So it happened in the case of the optimal, and it is happening in the case of the LRU also. So here we can also see that there is a stack property followed. 0 is present here, 1 and 0 both are present in both the schemes, 2, 1, 0 are present in both the schemes, means with the 3 frames and with the 4 frames as well. Similarly 3 to 1 is present, 3 to 1 is present here also. 0, 3, 2, 0, 3, 2 is present in the 4 frame as well. 1, 0, 3 is present here and 1, 0, 3 is present here as well. 4, 1, 0 is present here and 4, 1, 0 is present here as well. 0, 4, 1 and 0, 4, 1. 1, 0, 4, 1, 0, 4. 2, 1, 0, 2, 1, 0. 3, 2, 1, 3, 2, 1. 4, 3, 2, 4, 3, 2. So here clearly you can see that those pages which are present in the 3 frames are present in the 4 frames as well. It means this scheme is following the stack property. So whichever scheme will follow the stack property, the Belady's anomaly will not be affecting that. Okay, it means those which follow the stack property, if you increase the number of the frames, then the number of page fault decreases. Okay, now there are some of the schemes in which the Belady's anomaly happen, or you can say that those do not follow the stack property. For example, the first in first out scheme. If we allow the first in first out scheme, in that case the number of page faults may also increase. For example, for 0 there is a page fault, for 1 there is a page fault, for 2 there is a page fault, for 3 there is a page fault, we are sending 0 to bring 3, for 0 there is a page fault, for 1 there is a page fault, for 4 there is a page fault, for 0 there is no page fault, for 1 there is no page fault, for 2 there is a page fault, for 3 there is a page fault, for 4 there is no page fault. So number of page fault occurred because of the 3 frames are 9. Let us see how many page faults will take place when the number of page frames are increased to 4. So for 0 there is a page fault, for 1 there is a page fault, for 2 there is a page fault, for 3 there is a page fault, for 0 there is no page fault, for 1 there is no page fault, for 4 there is a page fault, so the number of page faults are now 5, for 0 there is a page fault, for 1 again there is a page fault, for 2 again there is a page fault, for 3 again there is a page fault, and for 4 also there is a page fault. So you can see that when you increase the number of the frames, the number of page faults have come to 10. In the earlier cases, when we were increasing the number of page faults, the page replacements, or sorry, the page faults were decreasing, but here it has increased. So the FIFO algorithm actually falls in the Belady's anomaly. And why is it happening so? Because you can see with the example 0, 0 present in both, 1, 0 present in both, 2, 1, 0 present in both, 3, 2, 1 present in both, 0, 3, 2, 0, 3, 2 is present in both, 1, 0, 3, 1, 0, 3 are present in both, 4, 1, 0, 4 is present, 1 is present, but 0 is not present. Similarly 4, 1, 0, 4 is present and 0 is present in 4 frames, but 1 is not present. So here you can see that there are some of the situations where the stack property is not satisfied. So in case the stack property is not satisfied, it will fall under the Beladi's anomaly. So that's why in the FIFO algorithm, when we increase the number of the frames, the number of the page faults increases. So this actually is the Beladi's anomaly. Now let us look at the page fault again, and we have seen in various occasions that the page fault is not desirable for us. What is the meaning of the page fault? That a page is referenced and that reference page is not present in the main memory. So how we will come to know that a page reference is not present in the main memory? We maintain a page table. In the page table, there is an entry known as the valid and the invalid. So if the valid and invalid bits set in the page table is V or I, or you can say that 0 or 1. So let us say we are saying that 1 is the valid and 0 is the invalid, okay, and a page is referenced. So when a page is referenced, then if we come across the invalid bit or the 0 bit, that means that the page is not present. So if the page is not present, we will have to bring that page from the virtual space. So here there is a page fault. So we are declaring there is a page fault just because of watching the valid or the invalid bit, okay. And an organization is here A, B, C, D, E, F, G, H. These are the pages, and we are going to accommodate these pages in the main memory. But we will not be accommodating all the pages at the same time. Some of the pages will be there in the main memory and some will not be there. This depends on the number of frames you have allocated to the process. So let us say the 0 number page is present in 4 number frame, and 2 number page is present in 6 number frame, and 5 number page is present in the 9 number frame. All other frames are not present. So we have maintained a page table which is containing 8 entries, but out of this only 3 entries are valid and others are invalid. So what happens when we have a page fault? We actually take an action, and that action is actually we will bring a new page in the main memory and send the old page back. So this can be understood with this diagram, that there is a reference from the CPU. The CPU is referencing and we have encountered the invalid entry in the page table, okay. So there is a trap because the page which was referenced is not present, so there is a trap. So the operating system will see the backing store, or it will see the virtual memory and will bring the required page in the page in the main memory. So where it will be, it will bring at the free memory space, or if the free memory space is not present, then the old page will be sent back and the space will be created, and that the new page will be coming in that space, okay. So what will happen if we are actually doing the page replacement? When the page fault occurred, the CPU has to do, or the operating system also has to do a lot of job, or it has to do the additional task, okay. So when the page fault is occurring, then CPU has to do the additional task, or the operating system has to do the additional task. It has to refer to the virtual memory. So let us say we are saying that all these activities which are referenced as 2 to 6, let us say 2 to 6 is the page fault service. So lot of time is required for servicing for a page fault. So let us say PS is representing the page fault service time. If our page is present in the main memory, we will be referencing the page from the main memory itself. So let us say TM is the time for accessing the page from the main memory. But if the main memory or the page is not present in the main memory, then we will be doing the page fault service. So when the page fault occurred, I have to do the page fault service, and then when a page is there in the main memory, we have to access it from the main memory and send it to the CPU for the execution. But when page fault did not occur, means 1 minus P, we only have to refer to the memory. So this is actually the T effective, or you can say that this is the effective access time. So P here is representing the page fault rate. I have already explained the page fault rate. Page fault rate is in the fraction. Let us say 7 is the number of the page fault out of 10. So 7 by 10 is the page fault. So 0.7 will be the page fault rate, and the miss rate will be or the hit rate will be 0.3 or the time when the page fault did not take place. Okay. So, if you are considering that 7 by 10 is the page fault and page fault service time is let us say 20 nanosecond and memory access time is let us say 5 nanosecond. So, the effective access time in this scenario will be 25 into 7, it means 25 into 0.7 plus 1.5. So, whatever this is, this will be the effective memory access time. If we expand this formula even further, we will be finding some straight line equation. For example, 1 minus p into Tm plus p into Ps plus Tm. So, let us expand it, multiply Tm with both the quantities Tm, Ptm, multiply p with other quantities p into Ps and Ptm. So, these two will be getting cancelled out and we will remain with Tm plus p into Ps. If we rewrite it again as Ps into p plus Tm, here p is a page fault rate which will keep changing according to the system. So, this is a variable. Okay. Effective memory access time will also be a variable. So, the two variables are effective access time and page fault rate, but the constant will be the page fault service time and the memory access time. So, if we represent this with the help of a straight line equation y equals to mx plus c, so effective access time becomes y, Ps becomes m, p becomes x and Tm is c. So, here you can see that this is the Tm and there is a straight line. When the page fault rate increases, effective memory time also increases, but in no case the effective access time will be less than Tm. If there is 100% occupancy of the required pages in the main memory will certainly be referenced. So, this will be the case. Now, there is just a small example by which you can understand this or how to apply this formula. The formula is effective memory access time is equals to p into Ps plus Tm. So, p into Ps plus Tm. In this numerical, what is happening? The page fault service time is 10 milliseconds. So, 10 into 10 raised to the power minus 3. In a computer system with the average memory access time of 20 nanoseconds, it means Tm is 20 into 10 raised to the power minus 9. When one page fault is generated for every 10 raised to the power 6 memory references, it means the page fault rate is this much. So, this is 10 into 10 raised to the power minus 9 plus 20 into 10 raised to the power minus 9. So, this will be 30 into 10 raised to the power minus 9. It means 30 nanosecond is the effective memory access time. So, you can apply the earlier formula and you can apply the new formula also after the expanding as per the requirement. But you should remember that this formula is applied when the page fault rate is very less. Okay. You can solve this problem as well, and this is the reference for this lecture, operating system concepts by Silvershadge and Galvin. In the next lecture.